Okay. I think I'll do it this way. And let's see. Okay. There we go. Okay. Um, this is the notebook that I have been late to share. And I wanted to also make sure that you guys have, I'm going to go back to this real quick. I want to share at this level. I will put this in the pipeline class chat too, but this is in the folder that you already all have access to that I was putting my notebooks in for you guys. And I've tried to be very good about explaining what I'm doing in here. But this is really everything we've covered so far for fake data in classification and regression. So I really should have opened this one first. And I'll let that one open up. It's pretty big. There we go. And so you can navigate very quickly through this notebook, but it's probably a better way because I'm making notes as I go too. I would like you all to keep this unique to the class, not shared outside the class. There's reasons for that. For you that happen to visit from YouTube, it's okay. I just ask if you would, there's a reason we just want to keep it private for now. A lot of it's just because it's still in development. We wouldn't want it to go out half-baked because maybe they haven't heard as much data as you guys have heard. And we're in this section, feature conditioning now. And I believe that we did cover this last week where we went over some one-hot encoding and some ordinal encoding. And I think that you will find these very easy by going through these sections if you weren't here last week. Then we started to go over scaling features. And I think we've talked quite a bit about why we scale features. There's many reasons, but I want you to always feel free to ask me here or ask me in our Slack chat too. That would be great. And if you're watching this on YouTube, just reach out to me or Guy. We can add you to our family. That is our Slack work group. And we can send you links so you don't miss this class if you'd like to be live and ask us questions. Now, a point. At this level, I've showed some scaling routines, just very simple at this point with some fake data. But where we want to get to is a survey of common scaling methods. And this is where I went through a little bit last week. We'll go through more today. The only motivation for writing our own routines without using SciPy or NumPy or TensorFlow is so that we really understand what we're doing deeper. And so, of course, if I send in an array of variables and I sum those variables and then divide by the number of them, that's the mean. Standard deviation, a little harder. First, I determine the numerator when I come in. And am I working with a small sample or a large population? That will affect what I use in the denominator. That's what's going on here. So if it's close to the full population, if we've reached the central limit theorem, we just use the number of all of them. To bias away from that, we subtract by 1. That makes the denominator 1 smaller and just increases the variance estimate. And that's a good thing to do for that reason. If I've sent in the average, the mean, I don't need to recalculate the mean, but I can if someone didn't send it in. So if it's, by the way, this is a slick way to say not, this will be a negative Boolean wise, an empty string will. That's why I do this little trick here. Then before I go into this for loop that I'm going to add things up on this variable, sum squared, I'm setting it to 0 first. And then I'm literally just going through for each value and subtracting the mean and squaring it, because that's what we do with the standard deviation. Then I divide by n on that quantity, and I take the square root. So that is your standard deviation. Now, the probability distribution function, you can look this up in any textbook. I'm just doing a two-step method to calculate that. And you see, I was even anal enough about this code from scratch to define E and to define pi and use them directly in this equation down here. That's all I'm doing. Otherwise, you would have had math.exp to do an exponent, and it would have raised E to this power. Now, here's where it gets a little complicated. If in case you haven't had calculus, or you haven't thought about it in a while, or you've never done it digitally, the cumulative distribution function, CDF, is adding up the area in very small rectangles, the small rectangles that are bounded at the top by the probability distribution function. But to get the CDF by numerical integration, we're just adding up very small slices under the PDF curve. And that's all that's happening here. I start at X left, and for each time I go right, I'm just adding that small width. This is how wide that panel is that I'm adding up underneath that curve. And so there's the width. Here's the height of that panel. And then the panel itself is the area of y times the width. But where I need to calculate this x so I know what x to send in currently for the panel height that I'm getting. And then you see that I set CDF to 0, but now I'm adding each panel to that. Well, what's powerful about this is I can send in any x left or right I want. And by the way, the other function from SciPy doesn't do it this way. You have to think about it like you were using the old tables if you've taken probability and statistics. But this will do it directly. You can send in the x left and the x right, and it will give you that cumulative probability directly. Okay, and then I have this function for the histogram, and really it's just doing a bar plot. You can see right here, this is the main part of it, but I'm doing some fancy things just to divide things up. And by the way, I had to adjust this by trial and error. I would encourage you guys to step through this on your own, one little step at a time, to understand what it's doing, and then use that to enhance your own programming knowledge, but see if you can improve the way I coded it. I don't always write the best code that could be written. I try, and I refactor my code frequently, but don't be shocked if you come up with code you like better than mine. I frequently watch one of my favorite teachers online. Although I love to learn from him, I don't necessarily like the way he codes. Or when I'm studying coding solutions from others, I'll try it myself sometimes and compare to what they did. I oftentimes like my code better than theirs. Doesn't mean it's better, it just means I understand it and like it better. So please do that yourself too. Now, with all that, we can create our fake distributions. And this is super powerful. Now let's see how I'm doing that. I've got a mean, standard deviation I send in. I say how many points per value max. I should say max, but this, you'll see what that means here in a minute. So I'm calculating my own low here because I'm trying to create a whole distribution. So I'm sending in this sigma's value. That means how many standard deviations to the left and the right of the mean that I want to use. When you go out to 5, that's pretty much going to count for all of the probability. It's going to be very close to 1.0. So that's all I'm doing. Mean minus sigmas, 5 times the standard deviation, mean plus sigmas times the standard deviation plus 1, because I want to go to that last value. And then notice that I'm rounding to 0. And that's because I just want whole numbers for this particular set. Now then I go for X in range between low and high. I'm going to use that probability distribution function above. I'm going to send in X, mean, and standard deviation, and I get that specific probability at that specific point on the probability distribution function. And I use that. That's going to scale. That's a fraction. It's a decimal fraction. And I'm going to multiply that by number of points per value. So it's never going to be 1001, because it's going to be scaled by the probability at that point. And then you don't have to do the shuffle part. But after I create that number of values, I'm just adding it in. Now I could have done it with this shorthand thing, and you'll see later that I do that. But I'm just saying for I, range this, add that current X to my data. So it's like literally fake measurements. And by the way, I'm about to create fake heights of first grader students. Okay. So that's all it's doing. Well, I measured student 1 and it was this, measured student 2 and it was this. So I'm literally treating this loop like the measurements. Now, if we do it with SciPy, you see the only difference here is instead of calling the PDF function I wrote, I'm calling this SciPy stats import norm. And what's the norm? I'm calling from the norm class the PDF method. And I'm also sending it the mean and standard deviation. And they're the same functions. That's the only difference. However, I could have used more NumPy here and done some slicker things, but I kept it simple. Now I'm going to call each of those functions. And you see that I just called the SciPy here, but I'm creating the fake data and then using the histogram to plot it with this title and my X values, X label and Y label. Notice this little trick. If you want a 2-line title, you just need to do just like you would print. Okay, so it put it on the next line. Now, just to show a little more here, create probability distribution function. I wanted to show how you could just plot this by itself. That's all I'm doing here. So it's similar to what we saw above, but I just wanted to show you that you can, in fact, just plot it out without, this is the extra step to treat it like they're individual values. This is showing that probability distribution function. In other words, when I'm at an X of 35, it's coming up here, it's getting approximately 0.125 and multiplying that on 1001. And so you roughly get 125 values for that point. And you can see that that's really roughly what's going on here. Okay. All right. Now that we can create fake data, we can test our different scaling routines. So here's my, I'm importing standard scalar in this example. And that's the, I'm going to use that later. But here I'm just creating my fake data again, same way. I've repeated it. Now I'm going to define my own standard scalar routine. Well, how does standard scaling work? We've got our mean, our standard deviation, and for every value in our data, this is what's going on. For every value in our data, I'm going to take that value and subtract the mean and divide by the standard deviation. And that is standard scaling. It's that simple. if I use NumPy, you can see that I'm using the mean function from NumPy, and we could have used the norm function from SciPy. And I'm directly calculating these from the data. You see, I used my functions, but now I'm using NumPy's functions. And then because it's NumPy, I don't need a loop. This is literally a for loop, but it's done with list comprehension. So you can see the for loop is right here. If we were to write this out, we would have said XS equals an empty array. Then we would have said for this in data colon, and then this would be on the next line, but it would be appended to our empty array XS. So this is a shorthand for that. But here, literally, I'm doing all that in parallel. I'm taking all the data, subtracting that one value mu from it, from all that data, and then from that result, I'm divided by standard deviation, hence the power of NumPy or similar SciPy routines. And then I go ahead and return the standard, the average and standard, the mean and the standard deviation, and my NumPy scaled values. Here I say just XS to distinguish between pure Python and NumPy. And so I do a test. I check our pure Python scalar. So I create that, I sort the values. Didn't need to sort them. There's a reason I wanted to sort them though, and you'll see. Then I get unique values, and you'll see why here in a minute. And I sort those too. This is just a X scaled set. Set meaning, let's just look at the unique values. So then I plot my scaled values. But I'm going to do that against my NumPy function just to make sure I've got everything the same between the two. And notice that it looks like it's scaled the same, but I also do this differencing trick. I take for X1 and X2 in this zip together set of lists, where basically this is going to be an array of each XS and each X in PS in separate little arrays. I bring those out as X1 and X2. I subtract them, I square them to get rid of the negative effect. I could have also done an absolute, and then I sum them, and sure enough, the difference of all of those summed together is 0. So they're doing exactly the same math with negligible round off error. I didn't even have to round it. It was that good. But then I use the scikit-learn version. So first, I turn it into the proper NumPy type array. I instantiate standard scalar from, and it probably would have been better to have this down there, go way up here and show you we're using this now. So from scikit-learn, pre-processing, import standard scalar. There's the standard scalar. I'm instantiating it as std scalar. And then first I do a fit. Oh, you can do fit and transform separately. And we'll talk about that a little more later. But you fit, for example, on your training data, and then you never use fit again after that one time. You can continue to use transform, but you only use fit one time, because you want to only fit with one set of data. And so now I've got my standard scalar, and I look at a plot of that, but I also compare that to our pure Python data, okay? By the way, you notice I say PXSS here. That's because what I'm doing is after I get the results, I'm sorting them so that this will work correctly, because they all need to be sorted. And then I'm reshaping it back. I'm converting it back to the proper pure Python list. I'm sorting it. And that's all this means, is a Python sorted. I don't know why I put the little, oh, yeah, this standard scalar scaled. I guess that's why I did that. But notice this extra one. That's just so I could look at things if I wanted to. But here, I do the same thing, and sure enough, we exactly match scikit-learn. So I'm going to do that over and over now for the different scaling methods. So I won't go into that much detail for the other ones. Now let's look at the math for min-max scalar. And by the way, you can go through this notebook at will now on your own. Okay, what does min-max scalar do? First, it finds x-min as the min of all our data, the minimum of all our data. And then there's a data range. It's the max of all our data minus x-min. Now notice I set a separate line for this because I'm going to need it more than once, but I only needed max data once. So I just called it directly instead of creating an intermediate variable. Then the way you do min-max scaling is for each value in your data, for each x in our data, I'm going to subtract the minimum and divide by the data range. Now, as you can imagine, this is going to have a different final scale than standard scalar. And this is just the NumPy way of doing it. Here, I'm being lazy. I'm thinking I can program this once and use it over and over. That way I can do the conversion to a NumPy array in this function. And it's this simple. For the max of the data and the min of the data, I get my data range. And then for every data point, subtract the min and divide by that range. Boom. That is that simple. I could have made this one line. I could have put this part in the denominator. I didn't do it just because I wanted it to be more readable. And then I do the same thing I did above. I look at the scale, and sure enough, it goes from 0 to 1 with including 0 to 1, and this is what I expected it to do. The NumPy does the same thing, and I waited till below here to just compare it to the scikit-learn version. So here is the scikit-learn min-max scalar from pre-processing, and it exactly compares to our routine. So that just, again, the only reason to write these from scratch is to make sure you really understand what's going on. That's why we write these ourselves, but it's pretty simple, right? Okay, now we go to max absolute scalar. And trust me, we will get a little more complicated, okay? These are pretty simple. Max absolute scaling, we take in our data, we find our data max. Well, but it's the max of the absolute values. That's the key here. Let me pause for Guy's question.
Thank you, Tom. Tom, it's in fact, it's just a practical question. When and why I should use min-max scalar? And what is the, let's say, the practical reason for using it? And I think it will reflect on the absolute max scalar because it's it will be good to answer this question before going for that.
Yes, absolutely. So we have a famous comedian in our country, Bill Murray. He's quite old now, but he starred with his buddies in the famous movie, the original Ghostbusters. And Dan Aykroyd, playing Ray, a famous physicist, asked him, how are we going to pay for all this? And Bill Murray goes, I don't know, Ray. Takes a big drink of hard liquor and says, I don't know. So it's a comical way to answer your question, Guy. I don't know. But this is why we automate our machine learning pipelines. We have a development platform for our machine learning pipeline. We write our pipeline so we can try different mechanisms at each point. Now, sometimes it's really obvious that you want your values to be from 0 to 1 instead of from some negative span to some positive span. But sometimes it won't matter, and sometimes you won't know which scaling mechanism will do the best. So we try different ones. We start with one, but we program our pipeline So it's easy to put in the other scaling mechanisms. And the value of that is that you notice scikit-learn has the same mentality. They actually have pipeline routines, they call them that. And they actually, for every mechanism, they have a fit method, a transform method, and a fit transform method. So you see, each of the mechanisms have this mentality of, you need to train me, and then you need to use me. And sometimes you can go train me and use me directly. So again, to answer Guy's question, sometimes it's obvious because of the nature of your data. But even if it's not so obvious which scaling mechanisms best to use, it's still good to run through different mechanisms after you have the whole pipeline built. Now, Guy, you might have had another point you wanted to make, and I want to give you some more airtime on that if you do.
Yes, and just for the same, first I agree with you, and this is why there is a lot of our steps we are testing and repeating again to find the best tuning between the methods and even the values. Just to maybe, for example, if we consider image processing or image data sets of images, scaling somehow sometimes it will help to prevent from having explosion derivatives. That mean the values are very high, and then when you are scaling between 0 and 1 or -1 to 1, it will help you to keep it, and that make the training faster. Sometimes the vice versa, you need to scale it to the higher level. Why? Because you don't want the derivative to be vanished. So this is also another way. How and when there is no standard way or silver bullet to tell you that this is the method that we are going to use, but it's something that we will face when we are training our models, and according to that task, data type, and let's say nature of data, we can choose the scalar method that we need.
Exactly. And I liked what you said. There's another point here in my mind. One of the big reasons for me to scale my values, because by the way, if there's not a huge difference in numerical magnitude between your features, like let's say one goes from 0 to 100 and another one goes from 0 to 2 and another one goes from 0 to 50, your model's going to train perfectly accurately. But if you're trying to gain more understanding using linear and logistic regression by looking at the feature weights, those feature weights will be meaningless in telling you which feature is most important. So it's for that reason you're going to try to get all your features within the same boundaries. Because if you don't, you're not getting an accurate feel for which features are most important to the analysis. And so we try to use a scaling mechanism that gets all our feature variables on the same numerical scale. That, to me, that's the biggest key here. Now, max absolute scaling. First, we have to find the max of the data, but that's going to be a positive number. In order to get, let's say that the biggest absolute value is a negative value. Well, I have to take the minimum of my data and then take the absolute value of it. And whichever of these two is largest, that will be my data max. And then all I do is scale all my variables by that max absolute value. Is that perfectly clear to everyone? By the way, please don't be embarrassed if I'm saying this is simple, but you're missing something, because we're looking at code when we do this, right? And so sometimes if you're not super familiar with the statements in the code, it can be confusing. So just because I say it's simple doesn't mean it's simple to you right now. So please don't be shy about asking. But again, all it is, if there's negative values, this is going to get us the smallest of the values in a negative sense, but then we're looking at which is the max absolute value. So once we find that, and we do the same thing with, you see, it literally is a one-liner in NumPy. I just take the absolute of all the values, and I take the max of those, and I divide all the data by that. So that's all that's happening here. I create my distribution again up here, and then I go straight to it. I see that my pure Python looks good. It's kind of what we'd expect, but look, it's not like this one, which went from 0 to 1. Here, it's going from 0.75 to 1. Now, if I'd had negative values, it would have looked much different, right? Because I'm also scaling the negative values here. I'm not making them absolute, but this is a positive distribution. So play around with different distributions. It's just that there's no first graders in the world with negative height. That's why we're looking at it this way. And then if I compare it to my NumPy version, they exactly match. And then, yes, we understood. This is the key part. We know now exactly what max absolute scaling is doing in the scikit-learn pre-processing module. Now, big question for y'all here. Did I have to code from scratch to know what scikit-learn is doing? And Jonathan, I'm going to put you on the spot because you're such a good student. No, you know what? I'm going to put Yogita on the spot. Yogita, hopefully you're there. Can you come off mic? Oh, awesome. Can you tell us another way to know what scikit-learn is doing without having to see if we can code it the same way and match their results? What's another thing you could do? It's okay if you don't get it. I'm putting you on the spot, so sorry for that. But it's because you're such a good student.
I have no idea now.
That's okay.
Maybe not currently, it's not coming to me right now.
Do you think it helps to look at code from really good coders?
Yeah.
Of course it does. So you look at the source code. If you go to the documentation for a routine,
Yeah.
then there's a little link, see source code for all of these routines in the scikit-learn documentation. And I want to take a moment to publicly praise the scikit-learn coding team. Good job, guys. Your code is beautiful, it's elegant, it's easy to follow, and you have to deal with so many things. Here, we're just coding from scratch to understand better. You're coding from scratch to serve the world, and you're doing an awesome job. Thank you for that. And there's a case where I had to get into the source code. I was trying to code blind and compare. That's very powerful for understanding's sake. But to learn to also code better, look at scikit-learn stuff. Now, you wouldn't code it that way yourself unless you were coding for the rest of the world. They have to take a lot of things into consideration. Okay, now we get a little more complicated, but for much more value too. The robust scaler. And the robust scaler, we need to first find this thing called percentiles. And with robust scaling, we're only looking, when we look for the 50 percentile, that's the median. Now the median's different from the mean. It's just saying, if you have a group of values and you sort them in order of magnitude, if you look at the one in the direct middle, let's say we had an odd number of values, it's easy to find the one in the middle, that's the median. That's not necessarily going to be the mean though, because we may have some big values over here, small values over here that affect the mean being different from the median. But let's just say it's the middle value in the sorted array of numbers. Now, to make it easy, let's say I have 100 values. uh-oh, I have an even number. So the middle value is going to fall between 50 and 51. What do I do? When that happens, I just take the average of those two and say that's the median. Now, but for the rest of them, it's easy. Where's the 25th one? Oh, it's the 25 percentile is the 25th one. The 75 percentile is the 75th one. Now, when it's not that, that's when I have to get creative here. And that's all that's going on here. I'm looking for the special case where it's exactly 0.5. If it's exactly 0.5, I'm going to take the average. But for all other cases, I'm just going to round it to 0. And that's either going to round up or round down. And by the way, I think 0.5 usually rounds up, but I didn't want it to do that. I wanted to find the average of those two. So this just tells me where in the array the percentile value is. So I could literally put in 26 here and it would find it for me, okay? But we really only want the median, the first quartile and the third quartile. And the median is also called the second quartile, meaning quartile quarters, 25% at a time. So that's the cool thing about robust scaling. This is like box and whiskers plots, if you've ever looked at those. It's showing you the range. It draws a box. First, the box is the interquartile range. It's a box showing where the data would fit, going between 25 and 75% of the data that you're giving it. Then it draws a line inside that box for the median, for the second quartile. And the width of that box is the interquartile range. And then all the data that falls outside of that is shown with just little lines at the end point. So the screen, whoa, so mirror mode here, non-mirror mode. So you have to get those drawn. And what's great about box and whiskers plots or robust scaling is I'm going to have one go off the screen here. It can go way out due to outliers. So let's look at what that looks like. Now I call that percentile and I get our median, our Q1, our Q3, and our. You have to watch the screen for this. I'm saying our, meaning it belongs to us. And then the interquartile range is the Q3 minus the Q1. So with the scaling of robust scaling, we subtract the median from each of the points and we divide each of those differences by the interquartile range, and that is our scaling. So you can see, NumPy gives us a percentile function. Thank you, NumPy. And it does it all at once. I don't have to do anything fancy up here. I was doing all this. And so it's pretty clean. And then look, well, I guess I did do a list instantiation, but I didn't need to do this. Boy, I wasted my NumPy power here. What should I have done? It should have been data minus NP median divided by my IQR. That's all I needed to do. In fact, I won't recode that on the fly here. I'll let y'all do it as an exercise. So because I've shared this notebook with y'all, you can view it, but if you copy it, and then you can run it, your version yourself. So fix that for yourselves. And then so I recreate my data just to be safe. I did it this way so hopefully I could run it without having run the previous cells. And then I do my robust scaling. I do it with NumPy. So there's the first robust scaler I wrote, the NumPy robust scaler I wrote. And sure enough, they exactly match. Now, I don't have any outliers yet, but I really like the way robust scaling deals with outliers, because if you're heavy on one side with outliers, it'll still keep the bulk of the data centered where the others will shift. And we'll eventually get into some examples, maybe not today, but soon, of how good it does that way. And you can see that we exactly match Scikit-learn's robust scaler. So I really like robust scalar a lot, so much so that I made a new scaling routine, and it's related to power transforming. Now, when we do power transformer, this may be the last one we cover today, you can see that we start with standard scaling. And then the data that results from that, we apply these rules to. And these rules come from Yeo Johnson. Now, the other set of rules for power transforming come from Box Cox. And I just am not interested in them. You can go look them up and use them, but why am I not interested in them? They don't work with negative values, or that rule doesn't, set of rules doesn't work with negative values. And I didn't want to have to worry about that. So I just thought, I'm coding Yeo Johnson's method, and I won't worry if it's positive or negative. That way I can just always use Yeo Johnson. But these are the Yeo Johnson rules that I have highlighted. And I do a NumPy method too. I create each of these logical masks and I throw it in. And I'm going to let, by the way, you can look these up on Wikipedia, these rules, if they're not as clear looking at them in code. By the way, I see Python code like math now, like math symbols. It's almost easier for me to look at the Python code than mathematical symbols now. But these are just special rules. You can see the, just so you, why did you separate lam and duh with an underscore? Because lambda is a keyword in Python. So I didn't want to confuse Python with redefining their keyword. By the way, I've done that before. It wreaks havoc in your code, and I still accidentally do it sometimes. But so I've got my pure Python power transformer, my NumPy one. Again, it's just standard scaling followed by these rules that Yeo Johnson came up with. Very elegant. And then I create my distribution and I see what power transforming did it with it. I'm setting a lambda of 1, but the scikit-learn version actually finds what they think is the best lambda. And I thought, whoa, I'm going to forgo that and just do mine manually. But even though theirs is at 0.965 and mine is at 1, you can see that we very close, well, we closely match between our NumPy and PurePy, but when I call theirs, I'm still pretty close. This isn't 0, that's pretty small, right? E to the -5, so not bad. And you can see that the shapes look the same, and we've got to remember this scaling is estimates. If we're a little off from scikit-learn, from something we wrote ourselves, so what? As long as it's close. So you might think, well, what's the advantage of that? Well, we're getting to that here pretty soon. Now, before, I want to spend plenty of time on quantile transformer, so we'll save that for another day. Now, next week, we're not going to come to class. You're all invited to go to Data Science Go conference. And someone that I think you know will be giving a keynote starting right in the middle of our class time. And I want you to all show up and listen to that guy because he's a wimp. And if you guys aren't there to support him, he will be very hurt. And that's me. So please show up and listen to it's my best version. I'm just holding myself back to not present it to Geith ahead of time because I've worked so hard on it. And I want Geith to be able to say, Tom, that is the best version by far you've ever given of this talk. So I'm hoping, I'm not showing it to him ahead of time in hopes that he can be surprised by it. And I probably shouldn't have even said that much because now if it falls short of what he's hoping, he'll go, yeah, it was good. We'll see. But
well, best of luck with that, Tom. We'll be supporting you.
Thank you. And it'll cross over into mentoring time. So we decided to move next week's presenter that we invited. She graciously agreed to postpone because I said, Susan, I want my family to show up and listen to this because it spans between the middle of this class and the beginning of our mentoring time. And so I'll be the presenter of my material, and then we'll have a question and answer time after my DS Go question and answer time. And then you guys, we can discuss the contents of my talk. But I want to show you something in our, just in a couple of minutes. If you go over this other notebook and you go down to feature conditioning, and then you go down to examples of each scaling. This is a beautiful data set here, but this is what I really want to show you. I created an add outliers function here. You can define the sigma out, meaning how many sigmas is it out? It's 10 sigmas out. And what percent of the original data are you going to use for outliers? 10%. And here the standard deviation 0, means 0, standard deviation 1. So that's for default values. But I show how this would apply if I've got my create distribution and I add outliers. You can see I'm adding outliers here. And then I can see how standard scaling affects the no outliers and the outliers. And you can see how this is not centered at 0 anymore because it's affected by the outliers, and it also doesn't have this -3. Why? Because the standard deviation is so large, it made this too small. And so now it's not really, it's just not dealing with the outliers well. So you either take away the outliers and honestly report that you took them out and you're investigating them, or you find a scaling mechanism that can deal with it. So here's min-max scaler trying to deal with it, and you can see it's really obfuscating the scaling of the data. But then we get to max absolute, and it's really not better. But then we get to robust scaler, and I really appreciate this. This is still where our original median was, but I've got these outliers. And I just think that's awesome. It still keeps it centered pretty well, but it shows the outliers. Well, and we'll go over this more later. And I thought I had added some new headers for this to make this easier to navigate. But I want to show you, I'm pretty sure I have it in here. Robust power transform method. So right here, I'm using the fine percentile again. I'm using robust scaling. And now I have a power transformer that starts with robust scaling. And look at what it does. If I choose a good value, boy, I really like the way this is working. Please keep this quiet. This is a big reveal in Gaith and I's book. We make a point that, hey, make up your own scaling method. The point is to scale the data. But I'm in love with this one that we hybridized from robust scaling and Yeo-Johnson power laws. And it works great, but I wouldn't always use it. For example, if I have skewed data, the quantile transformer, that's when your distribution, let's see, if I go back over to this one, we had to create some skewed, now I create some fake skewed data. Well, what if you don't want to use any of the other scaling methods if you've got data that's skewed? But look at what the quantile transformer does. It's not exactly over 0, but this is close enough to use in your linear regression, and very, very powerful. So that's enough for today. We'll pick up here 2 weeks from now and go into quantile transformer, which might take the whole lecture, but will be